Hey guys, I want to make a video going over this problem that we did on this past Sunday. There's a capacitor problem and it's got a couple parts to it, so make myself big. So part AI has the two plates, and then they want you to draw vectors representing the direction of the field, right? So in the middle, most of the time, well, all the time, what I'm doing is I'm drawing little vectors that are straight. All your vectors in the middle are going to be straight on, right? They're basically all going to be parallel. Out on the edges, you get something called fringing, and so the field kind of curves here. It will curve. And so to show that using vectors and not actually curved lines, you just have a vector going this way and then maybe like a vector going that way, kind of something like this, to show that it would start fringing or turning like that. So there's the first part. Make myself small. I'm going to use this FET thing as well to kind of explain this problem. All right, so for the second part, AI, what happens is we're going to take these plates and we are going to decrease the separation. So the separation is going to be less than it was. And they want to know, if it's moved to the new separation, what magnitude of charge would be on each plate. Right? I like FET because I can actually fiddle with it and we can check it. Make myself big. Okay. So we take the two plates and we make them closer together. What happens? And so a lot of these problems that are involving caps, what I call capacitors, are going to do this, where they're going to have you make things bigger. Well, they'll make the plates bigger or smaller, or they'll make them closer together or further apart. And so what happens, right? And so for this, there's a couple of governing equations when it comes to capacitors. Capacitance is Q over V. V is voltage. Okay. C, capacitance, is also, and this one is a little crazy, K times epsilon naught times A over D. And we looked at these, but it's been a while. So these are kind of some of your governing equations. There's actually a third one, the electric field. Let's see, epsilon naught A, I believe. Yep. So these suckers you'll see a lot when you're talking about capacitance. Now, one of the things that's going to happen here, when you look at what's on the top and the bottom of a fraction, right, that'll kind of tell you what's going to happen. So for this middle one, capacitance, if the distance between the plates gets smaller, capacitance will get bigger, and the distance gets bigger, capacitance will get smaller. So those two things are inversely related. The area, this is a area, so if the plates themselves get bigger, capacitance will get bigger. If the plates get smaller, this will get smaller. This is the electric field, right? So you can figure out what's going to happen with the electric field. So for this problem, I'm really fiddling around with these two equations. So for AI, they want you to come up. Now, I didn't like this. It said calculate for AI, but you're really not. You're really coming up with your own equation, right? So they want to know about charge. So up here, what I'm going to do is I'm going to solve for Q, right? Q equals CV, okay? Now, what happens here is the switch has been closed, okay? And the switch is closed, and so we have charge. These things are charged up, right? And so what happens here, your voltage is not going to change because the switch is closed. And if the switch is closed, so if you have a battery, right, this is my voltage source, here's my capacitor. if I have a little switch here, right, and I go ahead and close it, then your capacitor is going to be at the same voltage. This plate is attached to that plate, and this little plate is attached to this plate. This is the positive plate, this is the negative plate. So the positive plate, they're at the same voltage. Those are at the same voltage. And so your voltage doesn't change. So what happens here, okay, is your voltage doesn't change. So V naught, V final, we just can call it V naught because it doesn't change. K is equal to 1 because there's air. There's no dielectric put in there in between those plates. Okay. Epsilon naught is a constant, and we can use that. Okay. So Q is equal to CV naught. C is equal to all this stuff, right? So whatever I get here, I'm going to take and plug it in here. The area of your plates, each plate has an area of, well, each plate is a rectangle with sides of L. So the area is L squared. That's an L. Is L squared, right? So this area is actually going to be L squared. The distance is now D2, because remember, we made the distance smaller. So if I take all this stuff and I cram it in here, I get Q is equal to epsilon naught, K is 1, times L squared over D2 times V naught. And there you go. That's the equation that they want for part A double I. Real quick, I'm just going to show you on FET for that part. Okay, we had to come up with that equation, but what does happen, right? So if we have our battery off and then we flip the switch, right, and then we get both plates are charged now, we have an electric field between the plates. Now, they said, well, what happens if you make the distance smaller? You had to come up with an equation for charge. So what happens to charge? Here's charge right here in the middle. Let me I'll turn off stored energy for a second. We have our electric field. I'll just turn that off for a minute. So what will happen to charge? If you make D smaller, right? Well, if D gets smaller, then capacitance will get bigger. And it was Q equals CV. V stayed the same because it's connected. The switch is closed. So V stays the same. Q equals CV. You see it behind me. Q equals CV. V stays the same. If D gets smaller, capacitance will get bigger, which means charge should get bigger. So if I make these closer, you see that my plate charge goes up right here. Watch it. It gets smaller, it gets bigger. So there you go. All right, so our plates are closer together. Now BI asks us, well, what happens if we separate them a little bit, not all the way back? What will happen to the electric field? Okay, so if I pull these apart just a little bit, what happens to my field? Make myself bigger. So there's a couple ways to do this. There's a quick way, there's an easy way, and a hard way, right? If you make the distance even just a little bit bigger, so distance goes up, it's in the bottom of this fraction. Voltage stays the same because the battery is still connected. Then your electric field has to go down. The strength of the field. Done. Or you can look at it down here. If the distance goes up here, capacitance will go down. Area stays the same. All this other stuff stays the same because the plates are still the same size. If capacitance goes down, voltage stays the same because the switch is still closed. Charge goes down. And here, if charge goes down, electric field goes down. So we're really just manipulating equations. But that's part BI. If I make myself smaller. And so we're looking at charge, right? So if we're looking at electric field. So here's my field meter. If I take this and I move it just a little bit apart, you'll notice that you see the field is getting smaller. So I had it here, and if I just separate them a little bit, see how my field gets smaller. So that's part BI. All right, guys, last part of this problem, B-double-I, is what happens if you increase that distance, but you disconnect, if you leave the switch open. In a lot of these problems, this is what they're going to do. So the difference is what happens when the switch stays open versus when it's closed, because different things will happen, right? So first of all, when you charge capacitors, you got to have a voltage source, and you can charge them, right? Now, I can then disconnect my voltage source, and here's what happens. The plates stay charged, right? We talked about this in class. Capacitors will stay charged for a long time. So, if we do this, right, so the switch is open, and now we're going to pull these suckers apart. What happens to our electric field? Let me make myself bigger. Okay. So the switch is now open. So the question is, what happens? Well, what happens to capacitance? Well, if we're making the distance even a little bit bigger, capacitance has got to go down. Okay. Now, over here, what happens here? Well, if capacitance goes down, what happens? Well, if this goes down, this is actually C over 1, right? And so it's in the top of the fraction. So if capacitance goes down, voltage goes up. It should go up. Voltage should go up. If you make the separation between those plates bigger, voltage will increase. Okay. Now, what happens here? Well, your voltage went up. So people will be inclined to say that the field will go up. But the displacement here also goes up. And those two things are directly related. You know, the more displacement you have, the more potential you have. It's just like if I take this marker and I raise it above the ground more, well, it'll have more potential, right? Or raise it even more, it'll have more. So because this is up and this is up, this should stay the same. Okay. Make myself smaller. Woo. All right. And I can show this, right? So here it is. The battery is connected. The plates are charged. I disconnect. Right? Now, if I increase this, we'll see what happens. First of all, we said that capacitance would go down. So watch this green. Watch this green one here. Capacitance gets smaller. See it? Okay. So capacitance goes down. All right. Now, what should happen to voltage? Where's my voltmeter? Here's my voltmeter. We have a certain voltage between these plates right now. 1.5 volts. That's the voltage of the battery. So if I increase the separation, look what happens. Voltage is going up. It's just like raising something above, you know, the surface of the earth. So voltage goes up. Okay. So my voltage went up. But my displacement also went up. Those two are comparable. And so my electric field should stay the same. So if I bring my electric field detector back, let's just see what happens. See, it doesn't matter what I do, or raise or lower this. You're not getting any more field lines. And they're not changing, you know, how close or how far apart they are. So your electric field doesn't change. I like FET a lot because you can fiddle with this and you can practice. For instance, what happens if we make the plates bigger? Would our field get bigger or smaller? Field gets smaller. Field lines are further apart. And what would happen to voltage if we make the plates bigger? Voltage gets small. They may not ask that, but they might ask about charge. So let's look at plate charge. What happens if, first of all, what happens if we separate these plates? What happens to the charge? Nothing. Plates are already charged. What if I make them bigger? Nothing. Plates are already charged. The only thing that can charge things is the battery. So charge stays the same. Now if we connect the battery and then I move things, well then things can change because the battery is connected. If the battery is connected, well now my electric field, what happens to it if the plates get bigger? You can't see it. Here we go. It stays the same. Voltage. What about voltage? What happens to our voltage? it stays the same. Still connected.